Hello and welcome to a new very interesting video. This video is about the differential amplifier, and the differential amplifier which I will show you in this video is not made out of transistors, or it is an integrated circuit like an operational amplifier as integrated circuit. It is actually made of vacuum tubes, of electron tubes. So the devices which you can see here, and I thought it would be interesting to show you a vacuum tube differential amplifier and what it does, how it works and so on. So before turning on the circuit, I will show you the schematic of the circuit, and I will show you how it works and basically how a basic differential amplifier works. So for that I have prepared this whiteboard for you. So now I will explain you how a differential amplifier works, what it actually is, and the circuit which I've built on the breadboard is actually this circuit here. It is made out of one 12AX7 tube. The 12AX7 contains two triodes, so both of these triodes are in one tube. And then of course I have these additional resistors here and two extra capacitors. If you want to know the values, here we have them. But first I will show you how this thing actually works. It's a differential amplifier, so it means that it amplifies the difference between its two inputs. Here we have the two inputs. The first input has the voltage V in 1 and the second input has the voltage V in 2. And then we have also two outputs, V out 1 and V out 2 are the voltages on these outputs. So this differential amplifier here is made for AC. You can also build such circuits for DC, but this is made for AC operation. That's why it has these DC blocking capacitors here. And yeah, let me show how this thing actually works. So let's say I put a sine wave like this on the input 1, and on the second input I connect the second input to ground. So let me do that. There we go. So this is now sine wave input, this is ground. And what do we get now at the outputs? It amplifies the difference between these two inputs. So we have signal here, we have nothing here, so the difference between something and nothing is this something. And then we have a gain, so it has a high gain. This specific circuit is not such a high gain. An operational amplifier I see has a very high gain. This does not have a very high gain, but it has a gain. And actually, if the input looks like this, then we get an output here, which is on output 1 is the inverted input and amplified, and on output 2 we get the same signal as the input in the same phase, but not inverted. And in this particular circuit it is a little bit smaller because it's not perfectly balanced, and I will show you why shortly. Okay, but before doing that, what would happen if we connect on both sides the same signal? So let's say I would connect this signal on both sides. If I would do that, then the difference between these two would be 0. So ideally the output of this thing then would also be 0, which is what this circuit does, but it does it not perfectly, and why we will explore later. So let me tell you very quick how you can compute the operating point of this circuit. Basically I won't go much into detail now because I already made a previous video of a two-stage tube amplifier which contains a pentode and a triode made of the so I've used the ECL86 for that, and basically I go much more in depth how to calculate something like this. But it's not a differential amplifier, it's a normal amplifier if you want to say. Yeah, let me just tell you, basically the current which flows down here to this resistor is the sum of both currents flowing down here. So and you can set these two currents here by computing this resistor value here, and you get this resistor value if you look up the data sheet of the tube. Then you find a characteristics diagram in which it is shown how high the grid bias must be to get a specific current, and this is always a negative voltage which should be on the grid, so we have a positive voltage here, and with this resistor, which has a very high resistance, the grid gets actually this potential, so then this potential here is higher than this potential, so therefore we have a negative voltage across here, and yeah, this negative voltage then, according to the datasheet, gives you a specific current. And actually one important thing here is that the current which flows to this resistor is not this, it's double of the current. So if you compute the voltage drop on this resistor, you have to use the double of these currents. These two currents are the same, so you have to use I plate 1 plus I plate 2 is IK, and IK is the current flowing to this resistor, and the voltage drop on this resistor gives you this current, but this is double of that current. So you have to make sure that you get that right for computing the operating point. And then on this resistor should act like a current source. So the higher its value is, or the higher the voltage drop across is, the better. But if it is too high, you get, well, not if it's too high, but it shouldn't be too high, because if it is too high, then you get not so much output swing here, because there's not so much voltage left on here. So basically how I set this up, I set it up to have about 50 volts on here, about 200 volts on here, which means that I have 100 volts on this resistor, 100 volts on this tube right here. So we have about, so we have the half here, so this, if this is 200, 100, 100, and to sum that up we get 250, and of course there's a little bit of a voltage drop, but since it is so small, yeah, it's almost 250, so I can simplify it and just say 250 down here. So basically that's the way how you can compute the operating point. You can do it your own, or here I have already laid out the values. So notice that this resistor here, this resistor is quite low because of its low voltage drop, and the other resistors are bigger compared to that. Okay, but now let me explain you how this thing actually works, and for explaining that I've drawn a simplified version of the differential amplifier. Basically I've removed this RK1, and here there's just a resistor called RK, which is this one here, because this is so low in value, so it does not really matter. And I've removed these two resistors, so we can simplify it for looking at the AC values, at the AC components which are flowing in this circuit, actually, because it has this has not a really big effect on the AC components. It is just for the operating point. So so we can simplify it, and I can explain it easier. First of all, let's think about the DC conditions of this thing. Here we have the DC conditions, and as I told you before, if there is nothing going on the inputs, then the plate 1 and plate 2 currents, so these two currents here, are the same. Okay, and of course the cathode current here, the common current here, is the sum of both plate currents, and this cathode current should be constant. So if it is constant, then this would be the best thing for this amplifier. Okay, so now it gets a bit more complicated. If you look at the AC values in this circuit, actually if we think about the AC components, then the cathode current down here, I write it in small letters, so small IK. Capital IK means the DC values, and the small ones are for the AC values. And the AC current flowing down here should be 0. So the DC current for operating point should be whatever we have chosen, for example 2 milliamps, but the AC current should be 0. So which means the following, that the AC current flowing down here is actually the sum of these two AC currents of I plate 1 and I plate 2, small I plate 1, small I plate 2. So if now the IK is 0, so we have 0 is I plate 1 plus I plate 2, we come to the conclusion that I plate 2 or minus I plate 2 is I plate 1. So the current which flows down here must be the same, which is the current which flows down here, the AC current again, and therefore if I have a signal on V in which causes a change on the current on this side, then like I wrote this loop here, we have also a change in current on the other side, but negative, and therefore we get on this side, this output is inverted compared to this output, but we get the same voltage but inverted on this output because the current in this loop is the same if the current down here is 0. But in reality, this cathode current is not 0 because we have a resistor here, and if the voltage here changes a bit, then of course it's a resistor, so the current here also changes a bit. So what's actually happening here is that the I plate 2 current minus I plate 2 current is equal I plate 1 minus I cathode. So from this loop a little bit of current, like I dotted it here, a little bit of current flows down through to this cathode resistor here, and therefore we lose a little bit of current. So I wrote it here in absolute values to get rid of the minus sign. So actually the I plate 2 current here is smaller than the I plate 1 current, which means that the output voltage 1 here is bigger than the output voltage 2 on this side. And this means in conclusion that the circuit is unbalanced. So we have a little bit of a difference of the output signal, and we will measure that later. There's another thing which is a problem, and this is a common mode. If the input voltage 1 and input voltage 2, both voltages, if these two voltages are the same, then the I plate 1 and I plate 2 current rises. And if again this current, the cathode current, the AC cathode current would be 0, if it would be 0, then these two currents would cancel themselves out. So if this and this is the same, so they would cancel out. But in reality this is not the case. I cathode isn't 0, so there's a little bit of current which is not 0 flowing through to the cathode resistor, and therefore V out is not 0. As I told you before, in common, if both voltages are equal, then we have the same minus the same should be 0. But if here we can see that actually the same minus the same is not 0, because we have some common mode going on in this differential amplifier. So that's enough for the theory. And now I will do some measurements to show you the circuit in action. For that I will connect my function generator to the first input, then I will connect ground to the second input. I will measure the first input with the oscilloscope, the first output with the oscilloscope, and the second output with the oscilloscope, and then I will explain a little bit what we see there, okay? So here you can see the circuit. I've moved the other tubes a bit out of the way so that you can see just what the circuit is made out of. So we have here one tube which contains 2 triodes, and actually that's it. I have already prepared something else which I will show you later, how we can improve the circuit actually. So if here we have the triodes, here we have a couple of resistors, the coupling capacitors, and actually that's it. Not much more to it. And yeah, now I will turn on the power supply, and then let's move to the oscilloscope. So here on the oscilloscope the circuit is still off, but the thing which you can see here is the input signal on channel 1, and I've adjusted the output of my function generator to give me 2 volts peak or 1 volt peak. So we have 500 millivolts per division, and we have 2 divisions, so this means 1 volt peak or 2 volts peak. And here this line are actually 2 channels. It's channel 1 and channel 3, and both channels are set to 20 volts AC, and the second channel is connected to the output 1 of the circuit, and the third channel is connected to the output 2 of the circuit. So now I will turn on the power supply and heater supply, and you will see how the tubes are heating up, and the signal will appear soon. So now you can see how everything is coming to life. Let me increase the volts per division so that we can see it a bit better. And the first thing that I will do is to show you how high the amplification actually is of this circuit. And if you look carefully, the first thing that you notice is that the channel 2, which actually corresponds to the first output, is a bit higher than channel 4, which corresponds to the second output. And for measuring the amplification, I will just measure the amplitude on channel 3, which is the second output of the amplifier. And since the input is 1 volt, then I get the amplification by measuring the amplitude of the output. So for that I turn off the input right now to have a clearer picture. So we have just the 2 outputs, and now I will use the cursors to measure the output amplitude of the second output. And the amplitude of the second output, the peak amplitude, is actually 55.4 volts. So this means that the gain of the circuit is actually a half of that, because we have peak, we have 2 volts, so we have to divide by 2, and this is of course 27.7. So this is our gain of the circuit. So it's not really high as mentioned before, but that's it actually. But now there's another interesting thing to note, which is if you look carefully, then you can see that the circuit is out of balance, because if I have the cursor here, you can see that the channel 2, which corresponds to the first output, is higher than channel 1. So this is exactly what we have expected. If you remember the explanation of the circuit, which I did on the whiteboard, then we get exactly what we expect, that the output voltage on channel 2 on the output 1 is actually a bit higher than the output on the output 1 on the output 2. So later I will show you how we can solve that, but first of all let us measure how high it actually is, so that we have something to compare if we do our improvement. So to measure how much it is actually out of balance, I will use an automatic measurement of the oscilloscope. So I'll go into the measurement mode, and then I will put on channel 2, I will put peak to peak, and on channel 3 I will also put a peak to peak measurement on. And to make it a bit more stable, I can turn the high-res mode on. So there we go. Now we have a quite stable result, and what we get is I stop it. So what we get is 59 volts on the first output of the differential amplifier and 55 volts on the second output of the differential amplifier. So you can clearly see that the amplitude is not the same, it's a little bit off, I turn on the cursors again just to show it you visually. So if I move the cursors like so, so here you can see the difference. So let's just look at the first cursor. Well, let me move the second down here. So you can see these cursors are on the peak of the first output, and of course the peak of the second output is lower. So this is exactly what we have expected actually, and yeah, what also the automatic measurement gives us. So let me just compute how far off it is, how much it is out of balance. For this, to compare it easier afterwards, I will divide the output voltage 1 by the output voltage 2, so which is 59 divided by 55.2, and this ratio is 1.068. So this value, just keep it in mind so that we can compare it later, because later I will improve the circuit and then you can see how much we have actually improved it. Okay, so now again the out of balance value is 1.068, and next I will show you something else interesting. And for this actually I turn off the power supply first, because don't work on the circuit when it's on, because it contains high voltages. I will now connect both inputs to the same signal to measure the common mode output. The common mode should actually be 0 as mentioned before, because if we subtract the same signal from the same signal, so 1 minus 1 equals 0 for example, but actually this thing will have a little bit of common mode output, and now we will find out how high this common mode output actually is. Okay, so for doing that, here you can see the oscilloscope screen again. Now everything is off. I will turn on the circuit right now. Okay, so now it's on, and I will turn on the function generator, and as you can see we have a common mode output. So what you can notice first is that there is no phase shift between the first and second output, which is of course what we have expected. If you can remember the explanation which I did before, then this is exactly what we have expected. But now let's see how big this common mode output actually is. So let me zoom in like so, and also sorry on this channel here. So both outputs are the same, which is what we expect, and I will write down the second output, which is 4.12 volts, and we can also compute the common mode gain, and this is very simple. We just have to divide the output by the input, so we have divide 4.12 divided by the input, which is 2 volts peak, and actually we get 2.06, so this is the common mode gain. At the beginning we have also measured the differential gain, which was 25.7, and we can also calculate something which is called the common mode rejection ratio, which is the ratio of the differential gain divided by the common mode gain, which is in our case the differential gain is 27.7, and we divide this by 2.06, and then we get 13.44. So the common mode rejection ratio is 13.44 in our circuit, which is not really good if you compare it with operational solid state operational amplifier, which you can buy, but we will improve it. No worries, we will improve it shortly. So now that we've seen that this circuit actually has some problems, some common mode problems, and also some balance problems, the question is how can we actually improve this circuit? So let me go back to the whiteboard. So the problem, as I've explained it before, is caused by the resistor down here, and the reason is that if we have a tiny voltage change here, then we have also a tiny current change on the resistor, and therefore it leaks a little bit of current down here, and this is the reason for the unbalance, and I've also explained the common mode before. So what we can do is actually we can increase the value of this resistor. We can make it bigger so that it has more voltage drop, and then the tiny voltage change here with the current change which it produces is much tinier than before. Okay, so if we double the resistor, for example, if we double the voltage drop, then we get a much lower current change if there's a voltage change on here, because the overall voltage is bigger. So the ratio of change therefore gets smaller. So and therefore we can improve it that way by making this resistor bigger. Another way to improve the out of balance problem would also be to put the potentiometer up here with the common contact of the potentiometer on the HD, and then we have this the two sides of the potentiometer right here, and then we can adjust the balance of the circuit manually. But if you do that, then you need to adjust it, and this is maybe not such a good solution. It is a solution, but if we don't want to have to adjust it, then we have to find another solution. And another very good solution for this problem is hiding under this paper here. So here I've drawn a solution for this problem. The solution is for the common mode problem and for the out of balance problem of this circuit, and it will make it much better. And I will show you this in the next video. So this was the first part of this exploration of the differential amplifier, and in the next video I will show you the solution for this problem. So yeah, you can maybe you can figure it out yourself, or you could try out some things what you could do to improve this. Yeah, but I will show it you in the next video. So stay tuned for my next differential amplifier video, in which we will reveal the solution for that problem. And thanks for watching, and bye.